Let's solve the fourth and final problem in this short series on calculating entropy change that takes place during a process. A system consisting of 2 kilograms of water, initially at 160 degrees C, 10 bar, undergoes an internally reversible isothermal expansion during which there is energy transfer by heat into the system of 2,700 kilojoules. Determine the final pressure in bar and the work in kilojoules. Well, let's lay out a storyboard for this problem. It was not given that this was a piston cylinder apparatus, but it did say that the water was involved in an expansion process. So I'm going to draw it as a piston cylinder, and we'll take the water molecules as the system that we're analyzing. And as always, when heat transfers energy into our system, it's taken as positive Q, and an expansion will be regarded as positive work. So here's the data we are given. The initial temperature is 160 degrees C, which is 433 Kelvin. The initial pressure is 10 bar, and the mass is 2 kilograms. Now, state 2 is at the same temperature as state 1 because we were told this was an isothermal process. And it actually means more than that. The temperature is constant at 160 degrees C throughout the process. It doesn't just start at 160 and end at 160. It's 160 degrees throughout the entire process. Another thing we know about the process is there is heat transfer of energy into the system and in the amount of 2,700 kilojoules. We're going to model this as a closed system, of course, with kinetic and potential energy changes regarded as zero. We were given that it is internally reversible, and because it's internally reversible, there are no irreversibilities inside the system during the process, and therefore the entropy production during the process is zero. And we also know, as we said before, it's an isothermal process and it's an expansion process. We are asked to find the pressure in bar in the work in kilojoules. But before we do that, let me introduce a new term, this word isentropic, and let's define it and investigate it a little bit. An isentropic process, I'm modeling as having characteristics of the corners of a triangle. So an isentropic process has 3 characteristics. It's a reversible process, meaning that there is no entropy production. Sigma is equal to 0. It's an adiabatic process, so there is no heat transfer, therefore Q is equal to 0. And it's a constant entropy process, so delta S is equal to 0. And so when a process has all 3 of these characteristics, as shown here on my isentropic triangle, then it is said to be isentropic. Now, if you go way back in the literature, you'll see there's used to be what is now an archaic definition of isentropic. It used to simply imply that isentropic meant constant entropy. And you could get that maybe from this word isentropic. Isothermal means constant temperature, while isentropic can be taken to mean constant entropy. But there was a problem with that definition. Suppose we had an irreversible system that undergoes a process in which entropy is produced. But then the process also has just exactly the right amount of heat transfer, removing energy from the system, so that this Q exactly removes the amount of entropy was created. Well, in that case, then delta S for that process would equal to 0. But we want to imply in an isentropic process that it's a reversible process. So it's not enough to just say that isentropic means constant entropy, because in that particular example I gave, the system was neither reversible nor adiabatic. So the definition was changed, and if you're reading old literature, just be aware of this. Now, it's further interesting to note that if I have any 2 characteristics of an isentropic process, then the third one is implied to also exist. So for instance, I was given a process that was adiabatic and reversible, then I would know that it's a constant entropy process as well. Or if I was given a constant entropy process that was adiabatic, I would know that it is also reversible. Now, on the other side of that is that if one corner is untrue, so let's suppose I've got a reversible process like we have here, but it's not adiabatic, Q is not zero. Well, if that is the case, then I'll know that this one is untrue as well. So I can tell in the problem at hand here, the delta S will not be zero. And then, of course, we do not have an isentropic process. We knew that as soon as we saw that Q is not equal to zero. So let's get back to the problem at hand, and we find that there are two ways to calculate the change in entropy for this process. Let me introduce the TDS equation that says that for an internally reversible process only, the heat transfer is the integral from state 1 to state 2 of TDS. That's the temperature times delta S. Now, in a constant temperature process, this easily reduces to the temperature times the change in entropy, which is to say it's the temperature times the mass times the change in specific entropy. So I can rearrange this equation and say that S2 is equal to S1 plus Q over mass times temperature. Let's plot this on a TS diagram. State 1 is given at 160 degrees C, and it's at 10 bar. And so I'm going to plot that on the TS diagram on this 10 bar line. And at 160 degrees C, we find out that this is a subcooled liquid, because at 160 degrees C, the saturation pressure is 6.178 bar. This state's pressure is higher than that, so it is the subcooled liquid. We also know the process path that it's going to occur at a constant temperature of 160 degrees C. So we know the path. I'm going to draw it as a solid line, which indicates that that is the actual path of the process. Now, state 2, I'm going to simply assume at this point is a saturated mixture, that it's somewhere under the vapor dome. We'll have to check this because that may or may not be true. But let's find out. Let's find the specific entropy at state 1. We'll go to the water saturation table at 160 degrees Fahrenheit. And again, because of the 10 bar pressure, we know it's a subcooled liquid. And so the specific entropy at state 1 is just that of a saturated liquid at the same temperature. So I get a value of S1 is 1.9427 kilojoules per kilogram K. Well, now we can calculate the entropy at state 2. We said it was just the entropy at state 1 plus Q over mass times temperature. Well, we have the value of S1. Q is 2,700 kilojoules. The mass is 2 kilograms, and the temperature is 433 degrees Kelvin. So I calculate that the specific entropy at state 2 is 5.0605 kilojoules per kilogram K. Well, back in the water saturation table at 160 degrees C, let's look for values of S sub F and S sub G, and we'll get both of these values here. And let's compare our calculated value of S2 to the values of S sub F and S sub G at 160 degrees C. And what we see is that S is in between the entropy of a saturated liquid and a saturated vapor. So true enough, we have a saturated mixture. And the first thing we always want to do with a saturated mixture is calculate its quality. And that's just S minus S sub F over S sub G minus S sub F. And we have the values. And I calculate that the quality at state 2 is 0.6485. And we were asked what the pressure at the final state was. Well, being a saturated mixture at 160 degrees C, the pressure is the saturation pressure at that temperature, which we found here when we were first looking in the table. It's 6.178 bar. That's the final pressure. Now, there is another method we could have used to calculate the change in entropy for this process, and that would be with an entropy balance. Now, the entropy balance simply says that the change in entropy during a process, it's the sum of the entropy transferred into the system by heat transfer, plus the entropy produced within the system. So you can see that in these terms, that delta S is just the summation of Q over T, which is the transfer of entropy into the system with heat transfer. And notice also that entropy flows in the direction of heat transfer. So if Q is positive, indicating that heat transfers energy into the system, then entropy also flows into the system, plus the entropy production. So entropy can be increased in a system by being produced within the system. So we can solve this entropy balance for S2, and in our case, sigma 0, because it's an internally reversible process. Recall also that the change in entropy is the mass times the change in specific entropy. So I can rearrange this entropy balance and get that S2 is equal to S1 plus Q over mass times temperature. And that's exactly the same equation we just solved in our first method to looking at this problem. So we're going to get exactly the same value for the specific entropy at state 2. It's 5.0605 kilojoules per kilogram K. Well, now we need to find the work done, and we'll do that with an energy balance. In a closed system where we're ignoring changes in kinetic and potential energy, our energy balance is just delta U is Q minus W. Let me rewrite delta U as the mass times the change in specific internal energy, and that's equal to Q minus W. Let's rearrange this and solve for W, because that's what we're looking for. W is just Q minus the mass times the change in internal energy. So back to the water saturation table at 160 degrees Fahrenheit. We know that state 1 is a subcooled liquid. So the internal energy at state 1 will just be the internal energy of a saturated liquid at the same temperature. And a value coming out of the table for U1 is 674.86 kilojoules per kilogram. Now for state 2, I'll go to the table and get values of U sub F and U sub G at 160 degrees C. And we know that the internal energy at state 2 is just U sub F plus the quality times U sub G minus U sub F. We have all of those values, and we'll calculate that the internal energy at state 2 is 1902.8 kilojoules per kilogram. Now I can solve for work. Work is just Q, which is 2,700 kilojoules, minus the mass, 2 kilograms, times the change in internal energy. That's U2 minus U1. And I calculate that the work is 244.1 kilojoules.